This is my Physics 1 Lab 3 report. This lab has two parts. The purpose of Part 1 is to simulate the net force of a black hole on an orbiting star to find the mass of the black hole. In this case, the system is the star and the surroundings are the black hole. The purpose of Part 2 is to simulate the motion of a spaceship around a planet and its moon that is orbiting a star, which is orbiting a black hole, to determine the initial velocity of the spaceship. In this case, the system is the spaceship and the surroundings are the planet, star, moon, and black hole. The fundamental principles that we use in this lab are Newton's second law, which is also known as the momentum principle, which relates the net interaction between the system and its surroundings to the observed motion of the system. Because the main forces in this model are the gravitational forces of these circulating objects that point inward, we use the parallel component to determine the speed of the object and the perpendicular component to determine the direction that the object moves. So the main results of Part 1 is that the mass of the black hole is approximately 9.66 times 10 to the 33rd kilograms. You can also see the vectors of the Fnet, Fnet parallel, and Fnet perpendicular all in newtons. The main results of Part 2 is that the initial velocity of the spaceship, the x component is 0, and the y component is 150 meters squared. The moon's orbital speed was 668.33 meters squared, and the moon's orbital period was 2,350.33 hours. So these are the initial conditions for Part 1. Most everything was given to us. However, we did have to calculate the time interval between the imported data points. We did this by multiplying the 24 hours in one Earth day times the 60 minutes in each hour times the 60 seconds in each minute to get the delta t in seconds. So this is the code for Part 1. What we did for this part was we used the velocity components to define the initial and final velocities. And then we used those to compute the initial and final momentum vectors, used those to calculate the star's change in velocity and change in momentum to ultimately calculate the dp/dt. And because in this case, there is only one force, which is the force of the black hole on the star, that is equal to Fnet. Then we use that to calculate the parallel and perpendicular components, which we then use to calculate the mass of the black hole. In this model, you can see that there's a bunch of numbers down here at the bottom. Well, those are the masses of the star in each moment that we model in this computational model. And so what I did was I took all of those numbers and I averaged them to get an average mass of the black hole. I did the same procedure for Fnet, Fnet parallel, and Fnet perpendicular. So these are the initial conditions for Part 2. The main thing that we altered was the speed of the ship, the x component being 0 and the y component being 150. These were mostly chosen through trial and error. So this is the code for Part 2. What we did was we found the net force on the moon by both the planet and the ship. Then we found the net force on the spaceship both by the planet and the moon, and we used those to find the moon's velocity and position and the ship's velocity and position. As seen in the model on the left, the moon is modeled by the cyan color and the spaceship is modeled by the magenta color. And we can see that the moon is moving in a circular orbital path, and the magenta colored spaceship is orbiting around that moon without actually crashing into it. So any errors in this data and model can mainly be attributed to initial velocities being slightly inaccurate due to trial and error, as well as any human error while rounding the inputs that we put into the computational model. So what does Part 1 mean? So we know that net force and the rate of change in momentum are essentially the same. However, the net force is the observed force from the motion that is the real physical cause of that motion, and it points toward the center of attraction. The rate of change, on the other hand, of the momentum is what you compute from the position data. And like we discussed earlier, the parallel component changes the speed of the star, and the perpendicular component changes the direction of the star, which is what made it curve around the black hole. So in Part 2, what if we consider the entire system? So in this case, the system would be the black hole, star, planet, and moon. So what interactions must be included? For the black hole, we have to include the interactions between the black hole and the star, planet, and moon. For the star, we have to consider the interactions between the star and the planet and moon. And we also have to consider the planet and moon interactions, both ways. And this means that every object will feel multiple gravitational pulls at once, but the interactions don't matter equally. The dominant interactions in this system would be the black hole and star, which is very strong, and the planet and moon, which is strong in its own local system. And some of the weaker interactions would be the moon and the star and the planet and the black hole. That is all. Thank you.